Welcome back. In this video, we are going to introduce the concept of the residuals. And residuals are a way to determine how accurate our best fitting line or our model is to fitting data. So residuals are essentially how far off our actual data is from what our model would predict it to be, or our best fitting line. So here in example 1, we've got a young man who was injured in his football game. He went to the sports trainer for physical therapy to build up the strength in his leg. The table of the graph shows the number of repetitions he's been able to do each day he was in physical therapy. Well, this sounds familiar. The best fitting linear equation is y hat equals 2.05x plus 4.95 is shown. So here we've got our data in days, our repetitions, and our scatter plot with the data. And then we found our best fitting line, and there is our trend line. We did a linear regression, and we came up with our y hat, or our best fitting line. So the residual then, the residual is this red line. How far off is our predicted data from the actual data? So that is the residual. It's the vertical distance from the actual plotted point to that point on the regression line. And in the table below, we're asked to complete this information. So I took the liberty to fill in y hat already. All we did was take 1 and put it in for x and get our y hat. And we took 3 and we put it in for x and we got all of our y hats. So then our residuals is y minus y hat. So the residual here, y, is our actual y minus our predicted values. So that's what we're doing. That's our residuals. So our first residual is 0. Our second residual is negative 1.1 because we're doing y minus y hat. The next one, 2.8, and a negative 2.3 and 6/10, and that happens to add up to zeros. Now the square of those residuals, so we're just going to take the values in the column just to our left here, and we're going to square that, and negative 1.1 squared is 1.21, 2.8 squared is 7.84, negative 2.3 squared is 5.29, and 6/10 squared is 36 hundredths, and that sum is 14.7. So let's look at some vocabulary and definitions. I'm going to start here with the residual of a data point, since we've already talked about that. So the residual of the data point is the vertical distance from its y value from the regression line. Residuals help us determine if a curve is appropriate for the data set. So as we saw in our hamstring issue, our residual here is the distance from the data point to the point on the line. Now a deviation is a little bit different. Deviation of a data point is y minus y average, or the average y. That's what that y with the horizontal line is. So the directed difference from the average of the y's. Well, the average of the y's is way down here. That's just taking all of the y values from our table in the previous problem. It's taking all of these y values, adding them up and dividing by 1, 2, 3, 4, 5, dividing by 5. So our deviation is between the average and the particular point on the line. So our regression line, our line of best fit, is the least squares regression line, probably the line that gave us the smallest squares as we saw in our last table. And the residual is the actual minus the predicted, or if you want to see it in formula form, it's y minus y hat is our residual. And our error, which is vocab we haven't seen, it's these two flipped. The error is really the predicted y hat, because that's our predictor, minus the actual y equals the error. And if I interpreted the data right, the errors from our table then would just be the opposite sign. So plus 1.1, minus 2.8, plus 2.3, minus 0.6. Those are going to be our errors. In the next sample, we're going to use our graphing calculator to graph a residual plot and get a sense of what our residuals, or how far off our regression line is from the actual data. So we've got some data here, and we're going to create a residual plot. First, though, we're going to put the data in our calculator, and we'll create a stat plot, and we'll also come up with a best fitting line. So I have my calculator out, and I'm going to go ahead and enter the data into my list. So stat, edit, and I put 1, 2, 3, 4, 5 into list 1, and 2, 1.2, 3.6, 3.2, and 4 into list 2. So after I enter my list, I'll go to stat plot, I'll turn on plot 1, and I see plot 1 is on. I'm going to draw from list 1 and list 2. I will check my window. My x's go from -2 to 10. My y's go from -4 to 6. That seems to fit my data. And then I can go ahead and graph my scatter plot. Now we want to do our linear regression. So a little review of that. We can go back into stat, calc. We're going to do a linear regression. We're going to draw from list 1 and list 2. But now we're going to do something a little different. When we store our equation, we're going to go in the vars menu here. So right next to the program and the clear key, vars, and then we're going to go y and function. And we'll go ahead and store this in y1. And we can now calculate and store our best fitting line of 0.6x plus 1. So I go to y equals, and there it is stored. I can graph it, and now it graphs my best fitting line. Now we'll go ahead and graph the residual. So this is something new. We'll go back to the stat plot menu, and we'll go stat plot, and I'm going to go ahead and I'm going to turn plot 2 on. And now we're going to draw from list 1, but we're going to y list 2, we're going to go to second stat and residual. So that's where we're going to draw that from. And now we'll go ahead and graph. So now the red dots here, that is our residual graph. I could turn off my equation. I could close plot 1. And there is my residual plot. So we can see how far off we are. The new x-axis here would be perfect. If all our data was right on there, that would mean our trend line matches perfectly our data. But we can see here that some places our trend line underestimates, and some places it overestimates our data. And we'll talk about that in just a minute. So here in our notes, they give us 3 different videos or 3 different pictures of possible patterns in a residual plot. So on the far left, we have a random data here telling us that a linear model then is an appropriate model. And in these two, we have U-shaped and inverted U-shaped or V-shaped pattern that says a nonlinear model would be more appropriate. So let's take a look at a data plot with the least squares regression line and analyze the associated residual plot. We're asked to use a red pencil to draw line segments from the data points to the line of best fit at the right of this y hat. So y hat is that line there. And so all of these red lines are the directed distance. Well, this one's like 0. And what does that tell you about the value of the residuals? Well, residuals can be positive, negative, or 0. So residuals lie above the regression line, will underestimate. So for these guys, the residuals, we can see that y hat will underestimate the actual data. And below, y hat will overestimate because, well, y hat is over the data point, and underestimate, the trend line will underestimate when y hat is under the actual data. How do we know if our predicted line overestimates or underestimates our data? Use the residual plot of the data set to complete the statements. So here we have, these guys are positive residuals. So according to our graph, if our horizontal is our actual residual line here, y minus y hat, those would be data points that are exactly on our trend line. So these are data points that are positive, have a positive residual, so the actual data is above the residual line, as we can see here. So that means that our trend line, our predicted line, will underestimate because our predicted trend line is underneath those data points, where below here the predicted line will overestimate data when the residual value is negative. So this line is overestimating these points that are below the line. This line is underestimating these points. So that'll give you a sense of how a residual plot works and when we're overestimating or underestimating data. And we'll get some more practice with this when I see you in class.